Hello and welcome to our talk. My name is Guillaume Fournier. I'm a security engineer at Datadog, and today Sylvain, Baubeau and I are going to talk about a rootkit that we implemented using eBPF. If you don't know what eBPF is, don't worry, we are going to present this technology and tell you everything you need to know in order to understand the talk. Let's start with a few words about us. So we are the cloud workload security team. We usually use eBPF for good. Our goal is to detect threats at runtime, and everything we do is integrated into the Datadog agent. So the Datadog agent is an open source project, so if you are interested, feel free to check it out. That being said, for Black Hat, we decided to use everything we knew about eBPF to build the ultimate rootkit. So as I said before, we are going to start the talk with a brief introduction to eBPF. Then Sylvain will take it over to talk about how we implemented obfuscation and persistent access in the rootkit. After that, I will come back to present the command and control feature, along with some data exfiltration examples and a few container breakouts. Finally, Sylvain will present a few detection and mitigation strategies that you can follow to detect rootkits such as ours. Okay, let's start with eBPF. So eBPF stands for Extended Berkeley Packet Filter. So it is a set of technologies that can run sandbox programs in the Linux kernel without changing the kernel source code or having to load a kernel module. It was initially designed for network packet processing, but many new use cases were progressively added. For example, you can now use eBPF to do kernel performance tracing or network security, and more generally speaking, runtime security. So how does it work? eBPF is simply a two-step process. First, you have to load your eBPF program in the Linux kernel. And then you need to tell the kernel how to trigger your programs. So let's have a look at the first step. eBPF programs are written in C. So it's not exactly C, it's more like a subset of C because of many restrictions that eBPF has to follow. But I'm going to talk about this later. So once you have your C program, you can use LLVM to generate eBPF bytecode, which you can then load into the kernel with the BPF syscall. eBPF programs are made really of two things. The first thing is eBPF maps, and then you have the actual eBPF programs. There are a lot of different eBPF maps, so all you need to know is that they are the only way to persist data generated by your eBPF programs. Similarly, there are many different types of program, and each program type has its own use case. But regardless of the program type, each program has to go through the following two phases. First, there is the verifier step. I will talk about this later, but for now, just know that this is a way to ensure that your program is valid. And second, your eBPF bytecode will be converted into machine code by a JIT compiler. When those two phases succeed, your program is ready to be executed. Step 2 is attaching eBPF programs. So this is a way for you to tell the kernel how to trigger your programs. There are many different program types, so I can't present them all, but I'm just going to talk about 4 of them. For example, you can use kprobes to trigger an eBPF program whenever a specific symbol in the kernel is called. Trace points are similar to kprobes, but the hook points on which they can be attached have to be declared manually by kernel developers. Those two programs require another syscall called perf-even-open to be attached. The other types of programs I wanted to talk about are traffic control classifiers along with XDP programs. So those program types can be used to do packet processing whenever some network traffic is detected either at the host level or at a specific network interface level. Those two require a netlink command to be attached. So the only thing you need to remember is that each program type has its own setup and thus might require different levels of access. Another very important fact about eBPF is that eBPF maps can be shared between different programs regardless of their program types. All right, so the verifier. So the verifier ensures that eBPF programs will finish and won't crash. So to do so, it's really just a checklist, a list of rules that your programs have to comply with. So first, for example, your program has to be a directed acyclic graph, no unchecked differences, and you can't either have unreachable code. There is limits on, for example, the size of the stack of your programs, along with the overall count of instructions on your program. And finally, what I think, unfortunately, what the verifier is most famous for is cryptic output. So I'm sure a lot of you guys have already used eBPF before, but you will definitely know what I'm talking about. Yeah, if your program doesn't pass the verifier step, you are in for a very painful debugging session. Last but not least, eBPF comes with a list of eBPF helpers. So those helpers will help you access data or execute operations that you wouldn't be able to write natively. So in short, you have about 160 helpers today, and most of the heavy lifting of your eBPF programs will be based on those helpers. So for example, you have context helpers that will tell you things about the user space program that triggered the eBPF program, or other kinds of helpers such as map-related helpers or memory-related helpers that will let you read or write to memory. All right, so that concludes this introduction to eBPF, and I will hand it over to Sylvain so that he can kick off the presentation of the Rootkit.
Thank you, Guillaume. Before we get into the details, first let's see why eBPF is an interesting technology to write a rootkit. First, the safety guarantee brought by eBPF means that a bug in our rootkit simply cannot crash the host. An error in the execution will not cause any log message to be emitted. The user therefore has no way to know that something actually went wrong and notice the presence of the rootkit. As we saw earlier, the eBPF bytecode is converted into native code and the number of instructions is limited, limiting by extensions the performance impact that our rootkit can have on the machine that could otherwise be detected by the user. On a commercial note, eBPF is used by an increasing number of vendors for various use cases. With eBPF becoming widespread, the chance of one product being abused to load malicious programs also increases. The safety guarantee we just talked about should not give the security administrators the false feeling of security. As the set of features that is available for our eBPF programs is directly coupled to the kernel version, every new release brings new helpers and capabilities, we must carefully choose the right balance between the power of new eBPF features and their availability in real-world environments. Using helpers such as BPF-DPass or technologies such as KeyRSI would probably have made our rootkit easier to write. We decided, though, to use a set of features that would allow our rootkit to run on widely used distributions such as RHEL or the latest Ubuntu LTS. One of the primary tasks of our rootkit is to hide itself. What does it mean in our case? eBPF programs are bound to a running process. If this process gets killed, all the attached eBPF program will be unloaded. For that reason, it is essential that we both hide our program and protect him from being killed. The eBPF programs and maps used by our rootkit should also be hidden, and we should forbid other programs to gain access to them through file descriptors. So let's see our rootkit in action. So, we start our rootkit, which is kind enough to display its PID in the standard output. And then we look for this PID in the output of the PS utility, or in the proc file system root directory. And we cannot find any entry. We can also try to guess a file, and under this underpin hierarchy, same result. We can also use a relative path with the same results. Another way to detect the rootkit would be to send it a signal, like a user1 signal. And we can see here that it triggers an error, no such process. So, how does it work? So this obfuscation capabilities of our rootkit rely mainly on the use of two BPF helpers. First one, the BPF proc write user. This helper allows our eBPF program to write into the memory of the process that issues a system call. This can be used, for instance, to alter the data that is returned by a syscall. It is also possible to alter the data provided by the process as argument to the syscall. One caveat of this helper, though, is that the memory to be modified has to be mapped into the kernel address space, otherwise a minor or major page fault will be triggered, causing the call to BPF proc write user to silently fail. The other BPF helper is a BPF override return. This one makes it possible to change the return value of a syscall. It has an interesting property though. If the helper is used at the syscall return, it will simply change the return value of the executed syscall. Now, if it's used at the entry of the syscall, the execution of the syscall will be completely skipped. So let's look at how the obfuscation of a file actually works. At startup, the rootkit will populate a map with the path to its proc PID folder. Now the user space issues a file-related syscall, such as stat. These syscalls usually come in two forms. One that accepts the path to the file as a string. Another one that accepts a file descriptor for the file that the user space program must have previously retrieved using an open syscall. So let's consider the former. The path specified could be a relative path. Now, to properly identify the targeted file, the rootkit needs to do an accurate resolution of the path. Unfortunately, there is simply not enough context to do so at the entry of the syscall. So we need to hook deeper into the kernel in the VFS code. At this point, it's too late to block the syscall. Therefore, at the syscall exit, we need to change the return value to make the user space believe the call failed, for instance, and also scrub the content of the structures that were filled by the kernel. Now let's consider the later, the version that accepts a file descriptor. We do the same path resolution as before, but we pretend to user space that the call failed while storing the file descriptor that was effectively allocated by the kernel into an eBPF map. If the same process issues a syscall with the same file descriptor, we can, at the syscall entry, return an error and block the syscall. So, blocking the syscall that accepts a PID as argument is trivial using BPF override return. Same for loading kernel module. So now let's look at the obfuscation of our eBPF programs and maps. So, we use the BPF tool that is provided in the kernel sources, and it allows us to list the program and the maps loaded on the systems. And at this point, our eBPF rootkit is loaded, and we cannot see any map and any program associated to it. Now, if we start another program, an eBPF program, that is making use of maps and key probes, we can see the new probes, programs created and the new maps, but still not the one associated with our rootkit. So, the idea here is to hook into the BPF call itself, but two things are required here. First, to avoid the user space to iterate through the IDs of our entities, programs and maps, assigned by the kernel, using the BPF probe get next ID and BPF map get next ID. We also need to prevent user space from getting a file descriptor to the program or map from an ID that it might have guessed using BPF probe get FD by ID. So once these operations are handled by the rootkit, the user space is not able to view or modify our programs and maps. BPF probe write user is a crucial part of our rootkit, but it comes with a pitfall. When an eBPF program that makes use of it is loaded, the kernel prints a legitimate, though pretty scary message in the kernel read buffer. So let's look at how the rootkit handles this case. So we can look at the contents of the kernel ring buffer before the rootkit is loaded. And we can start a program, in this case it's cat, and it's a cat/dev/key message, and it will block and waiting for a new message to arrive into the ring buffer. We then start our eBPF rootkit. And we can see that the cat program exited because there was a new message inserted in the ring buffer. But that's not the one that the kernel inserted to warn us about the use of BPF probe write user. And we can also look at the whole contents of the kernel ring buffer and still not find the message. So in this demo, the cat/dev key message, journal D in our diagram, is blocked on read syscalls that will return once a new message arrives. So two eBPF programs have to be loaded by the rootkit sequentially. The first one, which doesn't use BPF probe write user, will hook on read syscalls and will make it return 0 and write legit looking messages into the ring buffer. After a short delay, the second program, this time using BPF probe write user, will be loaded. At this point, the read syscalls can be unblocked, and we can safely override the content of the first read messages with other legit looking messages. Now, another important task for the rootkit is to set up persistent access across reboots, for instance. For persistent access to the system, a generic method, close to the ones described in the obfuscation part, allows replacing the read content of some critical files, such as the SSH server authorized keys, or scripts executed by root daemon, such as crud or systemd. Persistent access to an application database can also be set up using another type of eBPF program called uprobes. So conceptually, there really are eBPF programs attached to user space function. In addition to being safer and easier to use than ptrace, they offer a valuable advantage. The kernel will automatically set up for us the hooks on every new instance on the program. So let's see an example targeting PostgreSQL. So we have a PostgreSQL server with a web app role with the bonsoir password, but we don't know this password, and we would like to get access to it using a randomly chosen password, in this case hello. So we start our eBPF rootkit, and it will set up the UI probes. And using a value inside an eBPF map, it will override the accepted value for the password. In this case, we managed to log in with the hello. So, the idea here is to hook on the MD5 script verify function of PostgreSQL that checks whether the user provided the right MD5 for its role, password, and the challenge sent by the server. Overwriting the expected hash contained in the variable shadow pass with a known value makes the comparison succeed and gives persistent access to the database to the attacker. Now, I will hand over to Guillaume that will show you the command and control capabilities of the rootkit.
Thank you, Sylvain. Let's talk about the command and control feature of the rootkit. So what exactly do we want to do? We want to be able to send commands to the rootkit to exfiltrate data and to get remote access to the infected hosts. Unfortunately, there are a few eBPF-related challenges that we need to face in order to implement those features. First, you can't initiate a connection with eBPF. Second, you can't open a port. However, eBPF can be used to hijack an existing connection. So in order to show off this feature, we have set up a very simple infrastructure on AWS. A simple web app was installed on an EC2 instance, and we used a classic load balancer to redirect HTTPS traffic to our instance over HTTP. The IP address of the load balancer is resolved from the blackhat.demo.doc DNS name, and in other words, the TLS termination is done at the load balancer level, which means that HTTP requests are sent to our instance unencrypted. So our goal is to implement CNC by hijacking the network traffic to our web app. First, we need to figure out which eBPF program type we're going to use in order to implement this feature. So although eBPF provides a lot of options to choose from, we decided to go with two different eBPF program types. So those two different program types are XDP programs and traffic control classifiers. Both of those program types are usually used for deep packet inspection. So while XDP works on ingress, TC works on both ingress and egress traffic. Another difference between the two programs is that XDP programs can be offloaded to network interface controllers, which essentially means that your program will be run before the packet enters any subsystem of the network stack. On the other hand, TC programs have to be attached to a specific network interface, which means that they are triggered much later in the network stack. With both programs, you can drop, allow, or modify a packet. And with XDP program, you can also retransmit a packet. So this option is super interesting because this means that you can essentially hide data from the kernel entirely, and you can receive and insert data to a packet even before it reaches any kind of network firewall or a network monitoring tool. Skipping the network stack also explains why XDP programs are mainly used for DDoS mitigation, because the overhead of the network stack is not there, and you will be able to drop packets much faster. As for TC programs, they are often used to monitor and secure network access to containers, or at the container or at the pod level. All right, so what you need to remember from this slide is network packets can be hidden from the kernel entirely, and data can be exfiltrated with an eBPF TC classifier because you can modify packets as they go out of the host. All right, so first, let's see how we used XDP programs to receive commands from the rootkit. So we implemented a client for the rootkit, and this client simply does, emits HTTPS requests to the rootkit with a custom rule, and a custom and data into the user agent. So after going through the load balancer, the request eventually reaches the host and triggers our XDP program. Then our programs parse the requests, the HTTP route, for example, and understand if that request is meant for us and not for the web app. After reading the user agent, the rootkit executes the requested command and moves on to the final step. So the final step is probably the most important one of this entire process. So the final step consists in overriding the entire request with a health check request. And we do so for two reasons. First, we don't want the malicious request to reach the web app or any kind of user space monitoring tool that might detect the unusual traffic. Second, we want the client to receive an answer in order to know if the request was successful or not. So as I said before, we could also have dropped the packet entirely. But since we're using TCP, the load balancer would have retransmitted the request over and over again until the request times out. So this would generate noise and increase our chances of getting discovered. That said, it would be a valid strategy for UDP packets. Let's have a look at how we can send Postgres credentials using this method. So on the left here, what you can see is two shells connected to our instance on AWS. And on the right, this is my local shell. So first, let's try to log into Postgres with the default password, which is bonsoir. So it works fine. Great. Now let's start the rootkit and do it again. And as expected, it won't work. OK, and the reason why it won't work is because we have hard-coded into the rootkit to change, the new password, and the new password is hello. So this time with hello, it does work. OK, so now let's use CNC to send the new password. So in this request, what you can see is that we are sending something to blackhat.demo.dog, and we are telling the rootkit to override the password of the web app role so that it now is Black Hat. So as you can see, there is a custom root, and then the data is put into the user agent. And this is the 200 OK from the health check. So we know that the request went through and that the eBPF kit did actually modify the password. OK, so if you try with hello again, it won't work. But this time, if you do Black Hat, it does work. OK, great. So, so this is how we can send a command to the rootkit. Now, let's see how we can exfiltrate data. So to exfiltrate data, the client has to send an initial request to specify what we want to exfiltrate. So the XDP part is basically the same as before, but this time the XDP program stores the network flow that made the request along with the requested resource in an eBPF map. And the reason why we do so is because when the web app answers the health check request, we want to be able to detect the packets that are meant to be sent back to our client. So when the HTTP answer reaches our TCP egress classifier, our eBPF program looks up the network flow and overrides the content of the answer with the file content if you wanted to exfiltrate file data or basically anything you wanted to exfiltrate. So now the question is, what can you exfiltrate with the rootkit? So everything we've showed so far work because we can share eBPF maps between multiple programs of multiple program types. And what this means is anything that is accessible to eBPF can be exfiltrated with the same technique. So for example, this includes file contents, environment variables, database dumps, and in-memory data. All right, so let's have a look at a small demo. I want to show you that we can exfiltrate Postgres credentials and the content of a file, such as etc password. All right, so again, on the left, you have the two shells connected to the instance on AWS and my local shell on the right. And as you can see, the eBPF rootkit is already running on the top here. All right, so all we have to do to exfiltrate Postgres passwords or credentials is make a request to blackhat.demo.dog and say Postgres list. So again, everything is encoded into the requests, and then eventually the rootkit will answer and tell you that 3 different roles were used since the rootkit was started, and you have the hashed passwords of those roles. So keep in mind that with Postgres, you don't need to have the clear password to log in. You just need the hash password. It's fine. All right, so now what I want to do is demo the other exfiltration example, which is the content of a file. Okay, so it's a 2-step process. So the way we do it is we tell the rootkit to start looking for etc password. And whenever a process in user space tries to open the file and read the file, then the rootkit will make a copy of the data that is read from the file as it is sent to the user space process, so that we don't trigger, we can't trigger anything because we are, we are using a process that is already starting trying to read the file. So this first step tells exactly that. So from now on, whenever a user space program tries to open etc password, we will be able to catch the data. So as said before, we need to, in order for the demo to work, we need the user space program to open the file. So let's just do that on the left. And now let's go back and request the content of etc password. And here you go. All right, so what's cool about this method is that it technically applies to any unencrypted network protocol. So for example, we also did it for DNS, and this method can be used, for example, to override either the requested domain name or the IP, the resolved IPs. So yeah, basically you can do DNS spoofing with this. All right, let's move on to our container breakouts. So this first container breakout works because the rootkit can detect and take over pipes between two processes at runtime. So we have two variants of this breakout. And we can do this either with kprobes or trace points. And the reason why this breakout works is because kprobes and trace points are not constrained by namespaces or cgroups. So if you successfully load a kprobe from a container, and if with this kprobe you can trick a user space program into executing code, then you essentially have found a new container breakout. So let's talk about required access. So as said before, we assume that you have potentially breached a service that has access to eBPF. This means that this service has at least cap sysadmin, or cap BPF and cap performance, depending on the kernel version. And then we add other kernel capabilities because we want to demo this container breakout through command and control. So you also require cap sysresource, cap netadmin, and to share the network namespace of the host. Again, this line is optional. This is because we are going to demo this container breakout with command and control, but you don't need those to break out. Then the default second profile can be activated. And finally, depending on the variant that you want to use for this breakout, you might need to disable AppArmor. So I'm not going to talk about how we catch pipes at runtime because I don't have time for that, but also because it's not that much interesting, to be honest. However, I'm going to explain what happens when we catch a process trying to read data from the receiver end of a pipe. OK, so let's take the example of a bash process trying to read from a pipe. So in a nutshell, we keep in an eBPF map a buffer of the data that we want to pipe to bash. So initially, this buffer contains what the rootkit was configured to pipe, so in other words, the payload. But then if you use the kprobe variant, we are able to append the original piped data to that buffer, so that when we are done writing the payload, we can seemingly start writing the initial data. On a more technical level, this means that we are going to send more data than what was initially written to the pipe. And to do so, we need to use the BPF override return helper. Unfortunately, this helper is only available to kprobes, and this explains why we have two variants of the rootkit. So if you want to have this feature, you would use kprobes. In other words, you would need to have to disable or at least modify the AppArmor profile so that you can actually access the sysfs file system so that you can register the kprobe. Or if you don't care about this feature, you can use tracepoint, which means that you don't need, you can lift the AppArmor profile requirement. All right, so let's move on to the demo. So on the top there, you can see, again, those the two shells to the remote host on AWS, and then my laptop is at the bottom here. And we're going to start a container with all the requested access that I've just talked about. So let's imagine that some kind of administrator was trying to install something and do this by fetching a script from a local server and then piping the output to bash. So this script is very simple. It's just IDE. So if you pipe it to bash, it will answer the UID of the current user. So let's start the rootkit now. All right, and then when it's done, we are going to configure the pipe data through CNC, so using the eBPF client. So you send a request to blackhat.demo.dog saying that I want to send you the data, and I want you to override data from if someone tries to pipe triggers a command that pipes data from curl to bash. And this is the data that should be piped instead of what was initially piped. Perfect, so you get the answer. So eBPF kit understood that, what needs to be piped now. And as you can see, if you pipe the data again, you can say that it's a ping instead of the UID as before. All right, so now I want to actually do something sneaky. I don't want to, show the user that, some random script was executed instead of what he wanted to execute. So to do this, I'm going to pipe the output of the ping to a file. And I'm also going to say, please back up the pipe data. So I'm going to add a flag to the request. Here you go. And this will tell eBPF kit to do the mechanism that I talked about, which is to pipe the initial data after our scripts. And here we go. If you do it again, you can see UID, GID, and you won't see that what our script was executed in the background. And if you look at the file, at the black hat file, as you can see, the ping is successful. All right. So now let's talk about our second container breakout. So this second container breakout is based on the fact that the rootkit can switch Docker images at runtime. So for this breakout to work, we added a uprob on the Docker daemon, and more specifically on the parse normalized name function. So this function is usually called whenever you make a request to Docker, and this function will parse the Docker image name from your requests. Once again, this uprob-based container works because, uprob container breakout works because uprobs are not constrained to namespaces or cgroups. And more precisely, as long as you have access to the file that you want to put a uprob on, the kernel will add the uprob to all the processes that actually execute that file, regardless of where they live. So what about the required access? So it's basically the same as the previous container breakout, with the only difference being that you need to share the host root directory with the container. So the truth is, you don't really need the entire root directory, but simply the Docker daemon binary. However, realistically speaking, this will only happen if the root directory is shared. So let's see how we leveraged this capability of the rootkit to break out of a container on Kubernetes. So whenever Kubernetes schedules a pod on the host, it will use a pose container to set up the network namespace of the pod and hold the IP address of the pod. So this container is meant to simply wait and will keep running until the pod is deleted. And because this container is not meant to do anything, Kubernetes does not really monitor it. So for example, it does not apply any kind of CPU or memory limits. In other words, this is a perfect target for us. If we can successfully take over this container, we will have a foothold on all the pods of the host, and this foothold will basically be invisible to normal Kubernetes monitoring tools. All right, so when you schedule a pod, Kubernetes will eventually ask Docker to run a pose container. When Docker receives the requests, it will try to parse the image name and will inevitably trigger our uprob on the parse normalized name function. At this point, our program overrides the image name, and Docker will realize that the Docker image Guillaume pose does not exist locally. So it will try to pull it from its configured registries, and if Docker Hub is one of them, it will be able to pull the image and eventually start the rogue container. Now, we had to deal with another tiny issue. We might have multiple instances of the rogue container, so we need to be able to control them through the rootkit so they do not all mine crypto at the same time. And to do so, we implemented a local API to communicate with the rootkit so that the rogue container can talk with, can talk to the rootkit and know what to do. So to send a request to the rootkit, you simply need to make a stat syscall on the file with a very specific pattern. And here, the request will simply be a ping, the rootkit will answer the action that this specific instance of the pose container should execute. All right, so let's see it in action. Okay, so on the left, again, as usual, this is two shells connected to the instance on AWS, and on the right, this is my local shell. So first, let's start by listing all the images that are on the host locally. So you can see it's mostly Kubernetes stuff and a Ubuntu image. Then let's schedule a new deployment. And this deployment is basically made just of one pod, which is a Postgres container. All right, so we need to wait a little bit for the container to be downloaded, since a Postgres container is usually quite big. All right, here you go. So now the Postgres container is running. So if you look at the different containers, you can see that there is a pose container of our Postgres pod, and this is the normal pose container. Great. So now what I want to do is uninstall the deployment so that we can do this again, but with the rootkit. So let's start the rootkit inside a container. So this is a new Docker container with all the access we talked about. And on the right, I'm going to configure the mechanism that I talked about before. So first, what you want to do is know which pose container is currently used by the cluster. So keep in mind that different Kubernetes versions or different clusters can run different pose containers. So it's not always going to be kates.gcr.io/pose. The next thing I want to do is I want to configure the rootkit to tell to tell the root container what action to take when that root container starts. So ping 0 will simply mean answer that the pose container should behave as any normal pose container. Then what you want to do is override the pose container as seen in the list before with our rogue pose container. Perfect. So now let's go back to our host and schedule a new deployment. All right, so let's list the different pods to make sure that the pod is actually starting. Here you go. And if you look at the containers this time, you'll see the Postgres container, but you will also see our own rogue pose container, which is the pose container for the Postgres pod. Great, so let's uninstall the web app again and try to play with the ping parameter. So instead of saying 0, this time we are going to say 1. So what 1 means is crash the pod. So what it will do is simply crash the pose container. And what's interesting is that we will see how Kubernetes behaves, and we will try to look for hints that will tell you why your Postgres container is in crash loop backoff. So you might want, for example, to describe the Postgres container. The Postgres pod, and what you can see is there is one specific log line that will tell you that a container cannot start, but you don't really know what it is. And most definitely, you do not see the pose name. And if you look at the restart count from collected by Kubernetes, as you can see, it's associated with Postgres instead of the pose container. So this makes debugging even harder for administrators. All right, so now we are going to stop the crash loop, and we are going to change the ping 1 into ping 2. And what ping 2 does is simulate a crypto miner. So as you can see, once I send the ping 2 miner, eventually you'll have the pose process that is using a lot of CPU. Again, the rootkit has the ability to hide processes, so we left it here so that we can see it for the demo, but we could also hide this process so that you can be using a lot of resources without anyone being able to know about it. All right, that's all for our container breakouts. I hope you had fun, and I will hand it over to you, Sylvain, so that you can present detection and mitigation strategies.
So, how can we detect and protect ourselves from this kind of rootkit? We should do this at different levels. First, if a vendor provided you with eBPF programs, you should go through an audit and assessment phase of their programs. Strong chances are that the code has to be GPL, as it probably uses some internal kernel symbols, so you can ask for it. What should you be looking for? Well, the program types that are used, the eBPF helpers they use, the communication through maps between programs may indicate a potential risk in the case the vendor program is compromised. We developed a tool to assist in this auditing phase. By inspecting the health files containing the eBPF programs, it is able to list the entities, programs and maps, and compute a graph of the interactions between them. So the tool was run on our rootkit with the following result. We can identify on the graph that the XDP program is storing information into a map that is also used by some key probes, which corresponds to the control and command capabilities of the rootkit. It is also possible to mitigate at runtime the loading of such programs by monitoring calls to the BPF syscalls and log the usage of it. It would even be possible to protect the BPF syscall by either restricting calls to it only to some trusted processes, or have the programs inspected before loading and rejected if they contain suspicious patterns or make use of some dangerous helpers. We could also compute and validate the signature of the programs before loading. An initiative exists to add this verification logic to the kernel itself. Using TLS everywhere for network traffic, that also helps mitigating the risk of rogue eBPF programs that may intercept network data. Now, if we were not able to block the loading of such a rootkit, how difficult would it be to detect its presence? Even if it's possible, though very challenging, to write an almost perfect eBPF rootkit, we should concentrate on the action that the rootkit would have to either block or lie about the results of such actions. For instance, our rootkit disables the loading of kernel module because such modules have the ability to list the eBPF programs and the active keystrokes. Now, let's imagine that we insert a module that executes specific actions known only to us. The blocking of the module by the rootkit would then be easy to detect. Monitoring the network traffic at the infrastructure level could help detect hijacked connections or strange packet retransmission. Our rootkit being far from complete and far from perfect, it should be relatively easy to detect it. That being said, we hope it will bring to light the potential and the risk of such eBPF-based rootkit while presenting some interesting techniques. So the code of both the rootkit and the monitor is available at these URLs or will be published in the next few days. Please have a look. Thank you for your attention and have a great Black Hat conference.